Okay, let's dive in. Calculus, right? Differentiation. How on earth does that connect to something like, well, drying food? Seems like a stretch.
It does, doesn't it? But it's actually a really neat example we found in some notes we were looking through.
Notes, what do they say?
Yeah, specifically a section called food drying differentiation.
Hmm.
And the main thing they hammered home was the importance of understanding the rate of moisture loss.
The rate of loss. Okay, not just that it loses moisture, but how fast.
Exactly. And according to these notes, getting that rate right is crucial for preserving food properly, which ties into, bigger things like food security.
Right, right. Because drying isn't just drying, it's more complex.
Yeah, think about it. The speed moisture leaves isn't steady. It changes.
Yeah.
And if you mess up that rate, well, the notes mentioned issues.
Like what?
Like drying too fast can create this hard shell on the outside. Case hardening, they called it. Traps moisture inside.
Oh, okay. That sounds bad.
And drying too slow. That just invites mold and spoilage.
Yeah.
So, yeah, the rate is critical.
So our mission here, based only on these notes we have, is to really unpack why this rate is the key thing and how differentiation, mathematically, helps you grasp it.
Hmm.
The notes seem to pitch this as like a solid example for college students learning calculus. Yeah.
That's the angle. Think of moisture content as M and time as T. So you might have a function MT showing how moisture changes over time.
Okay.
Differentiation, that's DMTT, gives you the instantaneous rate of change, how fast M is changing at any specific moment.
Ah, okay. So it's not just the average speed over, say, 8 hours of drawing. It's the speed right now.
Precisely. That's the power of the derivative here, because like we said, the rate isn't constant.
It changes.
It usually starts high, then slows down quite a bit as the food gets drier. Understanding how DMDT, that derivative, behaves gives you the full dynamic picture.
Got it. So if the rate is always shifting, you need a tool that can measure that shift moment by moment. That's differentiation.
You've got it. And knowing that instantaneous rate lets you control the process much better.
How so?
Well, you can figure out the best temperature or airflow needed at different stages to keep the rate where you want it, to avoid that case hardening or the risk of spoilage.
And that control, the notes suggest, is what makes drying effective.
Yes, directly impacting food security. Better preservation means food lasts longer, it's safer. It connects abstract math to, well, dinner tables.
So summarizing here, differentiation lets you quantify really precisely how fast moisture is leaving at any point.
Exactly. And knowing that rate, that instantaneous rate, is what allows you to optimize the whole drying process.
Optimization, meaning less waste, better quality.
Pretty much. Less spoilage, more consistent results. It's about managing a complex natural process using a mathematical framework. That's what the source material emphasizes.
Which really makes it a strong example for students. Like the notes pointed out, seeing calculus concepts like differentiation and integration used in something so tangible like food science.
Right. It takes it out of the textbook, doesn't it? Shows a real-world impact.
So it boils down to this. Using differentiation helps understand and control the rate of moisture loss,
Which is vital for effective food drying.
which in turn bolsters food security. A clear line from calculus to a global issue.
It's a great illustration from these notes, yeah.
Makes you wonder then, doesn't it? Think about all the other processes around you every day. Cooking, maybe conserving water, even managing finances. How many of those might secretly depend on understanding rates of change, using tools like differentiation, even if we never actually see the equations written down? Something to think about.